Right. Hello, everybody. This is Professor Iris Miano, about to give you your Week 13, Day 24 lecture video on the first two sections of Chapter 10. So, Chapter 10 is the very last chapter that we'll be covering in this course. Furthermore, Chapter 10 is from a separate textbook than the previous two textbooks that have covered the Chapter 2 material was its own textbook, and then Chapters 3 through 7 came from a different set of authors, different textbook. And then this last Chapter 10, Sections 1, 2, 4, and 5, not Section 3, doesn't exist in the textbook, will be from a separate different textbook and set of authors altogether. So you'll notice that there'll be, again, differences in the layout of the sections, and the delivery of the material will have a little bit of a different feel to it. Furthermore, Chapter 10 is all about formulas, basically. So in Section 1, we'll be covering perimeters and areas of polygons, which are one-dimensional and two-dimensional constructs, respectively. And then in Section 2, we'll cover circles. Again, in a one-dimensional and two-dimensional construct, we'll be talking about circumference, which is kind of like the perimeter of a circle, and also its area, and then those proportional chunks of those items as well in the form of arc length and area of a sector, which is just a piece of a circle. It's kind of like a pizza slice, so to speak. We'll get into that into detail in this section, these sections. And so the way that, that I present this is with introducing the formulas. You're going to write down the formulas, draw a pretty picture for each one of them in each of these two sections. And then we will have a litany, a plethora of examples associated with being able to effectively use these formulas that are being presented. So it's more or less a memorization game with these last four sections, but I hope that you are able to not feel so much like you are memorizing these things, but rather internalizing them, like they just become part of your brain relatively permanently. You'll definitely see these formulas as necessary in your future endeavors as a, higher level, transfer level mathematician, that's for sure. Okay, let's go ahead and get started with some formulas on perimeter. So perimeter generally for any polygon is going to be the sum of the outer edges of the figure itself. So let's start with triangles. That's the polygon with the smallest number of edges possible. And so here you see a generic triangle with side length edges of length A, B, and C. Add them all up and you get the perimeter, which here is being designated by a capital P. It's just as easy as that. So on your lecture notes, I recommend that in the space under the word triangle, you write down this formula, you draw yourself a pretty picture. Any triangle will do, and if you label the edges A, B, and C, then this formula will link up beautifully to it. Okay? Moving on to square. Yes, so squares, of course, as we know from Chapter 6, if I'm not mistaken, when that was first introduced, is a four-sided polygon. Interior angles are all right angles, and all of the outer edges are the same length. So you could just take that length denoted by lowercase s and multiply it by 4 in order to get the perimeter. S plus S plus S plus S. Even these last two edges right here aren't labeled. The assumption is that, of course, they are of length S. Add them all up, or just multiply that one length of S by 4, and you have the perimeter. And then rectangle. Rectangles are four-sided polygons, or quadrilaterals, such that the opposite edges are distinct measures and match across the way neighbors. You take two lengths and you add it to two widths. That's the perimeter there. Now, which one is width and which one is length? Does it matter which one is labeled L and which one is labeled W? Not even in the slightest. So, go nuts figuring out which one is supposed to be which, or just say to yourself, okay, one of them's W, one of them's L, and move on with your life, okay? Cool. So hopefully that's good for you. Area formulas. Okay, so just to be clear, before we move on to area, I want to specify that these formulas are indicating perimeter, which is just a distance around the figure. So if it's just a distance, it's referred to as a one-dimensional construct, which means that the units associated with them, think of any appropriate distance unit like inches or miles or feet or meters or something like that. It's going to be just the one-dimensional version of that unit. So if, the distance around of this triangle, let's say A, B, and C sum to 24, you would have to see what the units are. Let's say the units were meters. It would just simply be 24 meters. Okay, now when we get into area, though, this next section, that's going to be a two-dimensional construct. Okay? At some point in each of these area formulas, you're going to be multiplying some numbers together, and that's going to dictate that you should multiply the units together. So the units become squared. Okay, and in that regard, that's what I mean by saying that the units are a two-dimensional construct whenever you're talking about area. Okay, so here we go. Let's start off area with a triangle. Of course, we're going to redo the same three polygons that we just talked about in the area version of them. For finding the area of a triangle, you need two measurements. You need the base, which is usually represented by the horizontal trajectory edge, not necessarily horizontal though. And then the height is another way of thinking about that in terms of things that we learned previously is the altitude. The altitude of the triangle is also your height. You multiply them together, but then take half of that, and that's the area formula for a triangle. For a square, it's all in the name. You're going to take the side length edge, in this case S, lowercase s, and square it. Cool. So just multiply it by itself, and there you go. For a rectangle, you take the length and the width measurements, and you multiply them together. And remember, because these are area calculations, the units need to be squared. So let's say for the sake of argument that units for the square were, S equals, 3 or something, 3 feet for that matter. Well, then the area of that particular square would be 9 feet squared or 9 square feet. It doesn't matter in which order you say those two words, just so long as you say both of them in regard to being able to appropriately characterize the units for any kind of area measurement. Okay, it's got to be squared. Moving on, we also have the area of a parallelogram that we need to throw in the mix, and that'll be base times height, the height being the altitude of the parallelogram, which we went into some detail previously in class, in 2021 class, that is, to talk about how to draw an altitude for a parallelogram, and here you go. Multiply them together and you get your area. For a trapezoid. Now this is a polygon that we have not talked about in this class yet. This is the very first time that it comes up. A trapezoid, by definition, is a quadrilateral in which there are two parallel edges that are across the way neighbors from one another. That's literally the definition. That's the way we work with it. Now, the trapezoid that happens to be presented here is called an isosceles trapezoid because the base angles, the lower base angles and the upper base angles are a matched congruent pair of angles. So keep that in mind. But the most important thing that we want to glean from this trapezoid conversation is the area formula, which goes as follows. There is a top base and there's a bottom base. And the top base, even though it's being indicated pretty clearly in this figure that the top base, the B1, is less the length is shorter than in B2, that may not be the case. You might have your trapezoid kind of looking like the, flipped over version of this, and that's perfectly fine. But you'll take the bases, you'll add them together right here. That's this quantity right here. You'll multiply it by h, which is the altitude of this trapezoid, and then take half of that whole thing. That'll give you the area of the trapezoid. Okay? Cool. We'll have some examples in which we deal with trapezoid area a little bit later on in the lecture video, so stay tuned for that. And now we have exhausted all of the area and perimeter formulas that we're going to use in this section. So now is the time where we're going to entertain several examples. And so I stole these from the homework. These are not exactly problems that you'll be doing for the homework. They're like adjacent problems. So the numbers are very similar. The scenarios are similar, but they're a little different than the actual exercises that you are meant to work on. Okay? So for this first example, we want to find the perimeter of the rectangle in meters. Notice that they are specifying the units. Are the units, oh, hold on here. Check this out. The units are different from the length versus the width. So it's our job to recognize that and do a unit conversion. Now this is something that I am assuming everyone in this class is going to be able to do with relative ease, but let's have a brief conversation about the appropriate unit conversion that needs to happen for this one. Now, since they specify that the final answer needs to be in meters, notice that the length, I would call this the length, the 9 meter distance here for this edge, that's the length, and the width is 10 centimeters. So what do we need to do to this 10 centimeters in order to turn it into meters? That's right, we've got to, divide it by, what would it be, 1,000? Yeah, we got to move that decimal place over a few spots. So let's go ahead and talk about that in just a moment. But for now, I clicked ahead and I saw that the first thing that I do is reference the appropriate formula. Before I get even into any depth on trying to do the unit conversion, that definitely has to happen. But here I start with referencing the appropriate formula, which for perimeter of a rectangle, it's capital P for perimeter equals 2 lengths plus 2 widths. So then I'm going to go ahead and recognize that my width needs a unit conversion. So I go over, centimeters to meters, I divide by 100. I think I said 1,000 a second ago, my bad. No, you'll definitely divide by 100, in which case, because you need to use this unit conversion here. So notice that I am referencing here that I took my 10 centimeters, I took the 10 and I divided it by 100, and that allowed me to convert it to meters, because that's the relationship between centimeters and meters. There's 100 centimeters in 1 meter. So dividing by 100 to go from centimeters to meters is the right move, okay? So that's how I'm getting 0.1. Great. So 0.1 goes in for the width, because if you're going to use this formula, all of the input values have to be the same units. Otherwise, it doesn't make sense. You can't add together different units like that. You gotta do a conversion. So this is the way to go for that. And then you'll simply multiply individual terms there, the factors within the two terms, and then add the two terms, and that's how you get 18.2 meters. Remember, it's perimeter, so it should be just one-dimensional as far as the units are concerned. Notice that I don't have meters squared or cubed or anything funky like that. It is just a distance, so it should be just legit meters. And don't forget the units, okay? All throughout this chapter 10, we're going to be caring a lot about units because everything is going to have units associated with it, okay? So here we go. Continuing, next example. Let's say we have the perimeter of an isosceles triangle is 94 feet. Okay, so remember, triangle, 3 edges, we sum up the 3 edges, that's the perimeter, and it happens to be 94 feet. That's what that first sentence is saying. Then it says, each of the congruent sides is 2 feet more than 4 times as long as the base. So there's an algebraic relationship between the base and the 2 congruent edges of the isosceles triangle in question. We're going to find the length of each side of the triangle. How many sides does a triangle have again? 3. So that means we should have 3 answers associated with this exercise, with this example. Okay, first thing we should do is recognize that this problem did not come with a figure, did it? So we should draw a figure, and here is my offhand version of what this figure should look like. Notice that I just drew a quintessential, isosceles triangle, and I labeled the base with lowercase b. That's our main unknown here, because notice that the legs, the congruent sides, that is an algebraic representation of that base length. It's 2 feet more than 4 times as long as the base. 2 feet more than 4 times the base, which I'm calling b. So how do you represent 2 feet more than 4 times a number? Well, you call it 2 plus 4b in this case, where b is the length of the base in question. Okay, so you'll want to put your algebra hat on for this one in order to make that conversion happen. Oh, I went ahead and called it 4b plus 2. 2 plus 4b, 4b plus 2. It's representing the same thing. It doesn't matter to me in which order you present it. Notice that I mention 2 plus 4b as a more or less direct translation of what was being described here in the second sentence. However, when I was writing up this PowerPoint presentation, as you can see, I was thinking of it in more of a standard configuration of terms in which the, degree of the term goes from largest to smallest, whatever. That's an algebra thing. It's not necessary here. If you had translated it as 2 plus 4b as the length of the edges of the congruent sides of this isosceles triangle, you're still doing it right. Okay, now we want to take the algebraic representations of all 3 of these edges, add them all up, and set them equal to the 94 feet that was given to us, right? Because that's the way that we'll configure all of this information according to the context of the problem. Now, you can drop the parentheses around the 4b plus 2's at this point in combined like terms, and you will get a grand total of 9b there, and then the 2's add together to 4. We'll subtract 4 from both sides, divide both sides by 9, and we'll get b equals 10. Now, if you're being, tempted to just like box that up and call it a day, don't do it, because b equaling 10 is not enough information to address this exercise. It wanted you to find the length of each side of the triangle. So b equals 10 is just one length, right? It's that base length, but you want to remember that you need to affix the appropriate units for it too. So it's not enough to just go b equals 10, done. It's missing units, that one measurement, and you're supposed to be giving 3 measurements. So you need to put that b back into the 4b plus 2 expression and calculate the congruent edges as being 42 feet in length. So it would be appropriate, let me go ahead and move my thing over here, to represent it as 42 feet, and 10 feet. You should have 3 separate answers with appropriate units affixed. Okay, cool. That's it for that one. Moving on to the next example. Find the area of a square with sides 2.5 meters long. No sweat. Let's draw a quick picture. Here's a square. Each of the edges is 2.5 meters long. I only went ahead and labeled 2 adjacent edges. I know that to find the area, I'm going to multiply those 2.5s together, or square the 2.5, in which case I will get 6.25, and then you fix the appropriate units, their meters, and put the appropriate exponent on those meters. Because we're talking about area is a 2-dimensional construct, so the units have to be 2-dimensional as well. And the way to make your units 2-dimensional is to put the little exponent of a 2 on there, square them, and then you're good to go. It's really just that easy as far as finding the area of a square. As long as you know what the measure of one of the edges is, just square it and slap on the appropriate units. Done deal. Moving on. How many square inches are in 1 square yard? This is where it can get a little bit dicey, because you need to do a series of conversions in order to, unit conversions that is, in order to answer this question. And you need to kind of pull apart the idea of what a square yard is. Because if you have 1 square yard, that's 1 yard by 1 yard, right? And it's a square. Now, I don't draw a figure for this one, but I do pick apart these edges here and say, okay, let's say I have 1 yard squared, or 1 square yard is one way that you can represent this, and I pull it apart by saying, all right, that's going to be 1 yard multiplied by 1 yard. That's one way. That's like the easiest and most conventional way to think about this problem. Now, take those individual 1 yards and unit convert them into inches. Now, it might not be intuitive how many inches are in a yard, but I do know how many feet are in a yard. I know that there are 3 feet in a yard, so I'm converting each of these 1 individual yards into 3 feet and 3 feet. Okay, so now if I was trying to figure out how many square feet were in a yard, I would just multiply the 3's and get 9 square feet. But that's not what we're asking for. We're asking for how many square inches there are. So how many inches are in these 3 feet? Well, I know that a single foot has 12 inches in it, so if I have 3 feet, it should be 36 inches by 36 inches, right? So make that unit conversion happen, okay? Now we're ready to multiply the numbers together to get the number of square inches to answer the problem. answer the example, that is. So what's 36 times 36? Well, you can, grab your calculator for this. I'm perfectly fine with that. And you'll notice that 36 times 36 is 1,296. And then affix the appropriate units. In this case, it'll be square inches, or inches squared might be the way that you actually, intentionally read the IN with the exponent of 2, and that's perfectly fine. This inches squared, perfectly good way to talk about this unit. Square inches is another perfectly good way to describe it. You can't say those two words in the wrong order. Either way is good. Okay? And that's it for that one. This is one of those problems where it's so easy it's hard. It'll be hard if you don't know the trick, but if you're watching this lecture video, then you're seeing the trick here. So good on you. Next example, let's find the area of this rectangle. We are going to give the area in square feet. So there's going to be some unit conversions that are ahead, because look at the units of these edge lengths right here. They are in yards. So we need to convert into feet and then perform the multiplication. So that's what we should do first, right? Let's go ahead and recognize that 15 yards, this length right here, is equivalent to 45 feet. How am I getting that? Well, in every yard, there are 3 feet. So I should take the 15 yards that are presented as the length here and multiply it by 3 to get the equivalent number of feet. This is the unit conversion in play. Now, that being said, how many feet is equivalent to 7 yards? Well, that would be 21 feet, right? Just multiply by 3. Take the 45 and the 21. Those are the numbers you need to multiply together in order to get the area of this rectangle in square feet, as they asked. As such, okay? So there you go. Just a quick unit conversion is necessary in order to get the ultimate final answer of 945 square feet, or feet squared. Either way of describing that is correct. Okay, moving on. Find the area of the triangle. Okay, one thing you'll notice about this figure here is that there is a little bit more information than what you need, and that is pretty, indicative of some of the exercises in the textbook, and it's really kind of there to test your, knowledge of what you need in order to find, in this case, the area of the triangle. There's going to be sometimes information given to you that's not necessary. You need to, weed your way through that and figure out what you actually need in order to find the area. So recall that the area formula for a triangle is 1/2 the base times the height. So what would be the base here? What would be the height here? What is the piece of information that's unnecessary? Well, the base is this horizontal edge, the 18 feet, and the height is the altitude, the 6 feet. Notice that 12-foot long edge that's given to you there? Discard it. It's not necessary. You're not going to need it in the area calculation, because the base, like I said, is 18 feet. The height is 6 feet. Multiply them together, slap in a factor of 1/2, 54 feet squared, or square feet, however you like to read that. And that'll be your final answer there. So I am leaving a little bit of a detail out with some of the algebra, canceling out common factors. Basically, half of 18, like the way I'm thinking about this is that it's half of 18. I'll take that as a 9. 9 times 6 is 54. So, if you guys ever want to talk any more detail about some of the algebra associated with these homework problems, of course, I'm totally game to help you out with that. All right, moving on. Ooh, let's find the area of this triangle, and this one's a little bit trickier, but it's still, remember, same formula. Area equals 1/2 base times height. So we just have to be able to identify what's the base, what's the height. Is there any extra information here? Yeah, there is. And it's the 7 miles right there, that little edge of the triangle. Don't need that. You just need the height, which is given to you as that exterior altitude of 6 miles. And then the base distance is the 3-mile horizontal edge length right there. So multiply them together, take half of it. That'll be 9 square miles, or miles squared. Okay, cool. That's that for that one. Let's go ahead and take the area of this trapezoid. So like I said earlier, we can totally expect a trapezoid to kind of look like it's upside down compared to the initial way that was presented to us when we saw the formula being presented. Sure. Ultimately, what we just need to recognize is we have a base, another base, right? A 34-inch base, a 28-inch base, and then we have a height. So, referencing the appropriate formula, we have 1/2 of the sum of the bases times the height. So just plug and chug, folks. B1 is either 34 or 28. B2 is the other base. It doesn't matter which one because, addition is a commutative operation. You can do it in whichever order you want. And the height is the 16-inch length there. So put all those elements in play. I went ahead and said that the B1 is 34 and B2 is 28, but please recognize that you could switch those. You could have this quantity be 28 plus 34, and you're still going to get the same sum, right, of 62. You take half of that, 31 times 16, that gives you 496 square inches squared. Okay, cool. And that's that. And continue to remember that the units are being squared anytime you're talking about area. It's a very important thing for us to glean here. All right, moving on to the next. All right, let's find the area of this parallelogram. Remember, the area of a parallelogram is base times height. And the height is this altitude right here. The base is this 20 centimeter long edge. The base is always what's the word I'm looking for? Connected to, no, that's not right. Well, the height is always going to be, perpendicular to the base in question. So the base in question is the 20 centimeters, right? That's the thing that we want to grab, not the 9 centimeters. So the 9 centimeters is the decoy. That's the thing that's being thrown at you to see if you're hip to just taking the elements of the figure that are necessary for calculating the area. So, yep, your base is going to be the 20 centimeters, your height is the 8, no unit conversion needed, just multiply them together and take the units and square it, and that is it, literally. So 20 times 8, that's how you get the 160 centimeters squared, or square centimeters, however you like to say it. All right, next problem. Ooh, this is where it gets real fun. This is what we call a composite figure right here. They're not calling it that in this exercise, but definitely this is something that could be, I think that language is sometimes used in the sections at hand, and in chapter 10 that is. And and if it's not, that's okay. You might see it described in some of the things that you'll see in your higher level mathematics, transfer level stuff. We're going to find the area of the shaded region. So notice that we have an irregular pentagon. Do we have a formula for an irregular pentagon, or even a regular pentagon's area for that matter? No. But if we draw an auxiliary line, this line right here, the blue one, you might notice that the figure is cut into two very distinct pieces that we know how to find the area for individually, and that's a triangle on top and a rectangle down below. So find the so you want to, what do I like to do to describe this? I like to call this making a customized area formula. And this one has the area of the triangle plus the area of the rectangle. You're just simply going to add them together, and that'll give you the total area of the shaded region. So the base and the height for the triangle are 11 inches and 2 inches respectively, okay? And then the length and the width are 11 inches and 5 inches respectively. So just plug them into your custom area formula that we came up with and simplify it down, or slap on the appropriate units, in this case inches squared, and you're done. Okay? So these composite figures can be a little bit tricky at first, but it's important to, in your practice, come to a point where you can draw an auxiliary line to separate the figure into individualized regions for which you can find the area and then add them up. Okay? In this case, it was a rectangle with a triangle on top. Moving on. Now sometimes you will be doing kind kind of something similar to that. To find the area of this composite figure, we're going to take the area of the parallelogram that would be present if the dashed line, this region right here, was also shaded in. But then notice that it looks like we have a parallelogram with a triangle cut out of it. So for this one, our custom area formula is going to be the area of the parallelogram if it was like a complete figure with the dashed line stuff all shaded in, minus the area of the triangle that appears to be cut out of it. Okay, so that's the jam for this one. That's the trick. So here is my area, custom area formula, and notice that I'm using subscripts because there are two different heights that I want to capture here. There is the height of the parallelogram, which I'm going to call H1, and then there's the height of the triangle cutout that I'm going to call H sub 2. H1, H2, H sub 1, H sub 2. These are acceptable ways to describe these subscripted factors right here, okay? The base, however, for the triangle is the same base for the, this is the base for the parallelogram, the first term, is the same as the base for the triangle. So I don't need to have different values or subscripts distinguishing those two bases. They're the same value. They're going to be 17 millimeters no matter what, okay? Cool. So here is me plugging in the appropriate numbers and simplifying and fixing the appropriate units, which in this case will be millimeters squared, or square millimeters. So hopefully that's pretty straightforward. But you guys are going to let me know in class if there needs to be any more discussion about like the nuances of the algebra associated with this. But more or less, a lot of these problems are plug and chug. Reference the appropriate formula or create a custom one, as the case may be, and then plug in the numbers, simplify, 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 affix the appropriate units. Bob's your uncle. All right, moving on to, here is, I think this might be the last, it might be the last or the second to last example in this section. Excuse me. Right, and then we're going to have a bunch of stuff about circles after this, but here we go. Notice this really irregular, excuse me, figure right here, and also notice that we're talking about perimeter, and we want to find x and y and the perimeter of the entire figure. So you're going to take a couple of things into account here. In order to find x, which is this distance and this distance here, you'll want to notice that if I take this distance x plus this 5.29 inches and this other distance x, it lines up perfectly with this 12.17 inches. Like, think of yourself as like moving this wall all the way to the edge right here, right? Wouldn't it line up perfectly here? That's supposed to be the implication anyway. Furthermore, you can take as gospel truth this total edge of 13.68 inches, and then also add up the 10.41 inches to this y length. And even though if you were to put like a straight edge right here, it wouldn't quite line up. I think that's just like a little bit of a printing error on my part, but the implication here says those are supposed to line up. So you can go ahead and take your 10.14, add this y distance to it, and set it equal to the 13.68. That's how you're going to calculate the y distance. You're going to, and going back to the x, you're going to take two x values, add it to 5.29, and then set that equal to 12.17. That'll allow you to solve for x. Here you go. So here we go. There's your formula that you're going to use, your equation that you're going to create in order to solve for x. And then you get 3.44 is the value of x after you simplify it all the way down, and that's the algebra that you need. For y, we have 13.68 equals 10.41 plus y. And then you'll just subtract 10.41 from both sides, and therefore y equals a value of 3.27. Okay, x, check. Y, check. Ooh, now we need to find the perimeter of the entire figure. Yikes. So that's going to be a time-consuming endeavor, but you could go ahead and just follow along with me here. Check this out. Ooh, yikes. So here is the entirety, excuse excuse me, of the perimeter calculation for this particular composite figure. I started from this top edge right here of 13.68, and then I went around all of the edges clockwise. So notice that the next term is 12.17, that's this one here. Then the next term is 3.27. Where did I get that from? Oh yeah, I calculated it right here as the value of y, and so on and so forth. And then you just get all of those values all the way around, and you punch them into your calculator, I guess. And if you're not using a calculator, then you are going to be, what's the word I'm looking for? Yeah, doing, like, adding it all up by hand, like lining up decimal places, all of that good stuff. Yeah, I wouldn't give you anything too crazy on, like, the exam proper. There might be something to this effect on, you know, extra credit or something. I don't know. No, I'm not going to give that away. Yeah, you'll see. Anyway, so you just add up all these numbers up, and then you'll get this value here. Cool. All right. So, sorry. Like I said, that was the last example associated with perimeter and area of polygons, and now we're going to switch gears into the distance around and area of a circle. So here are the formulas associated with that, okay? Starting with circumference, which is another way of saying perimeter of a circle. It's got a special term, and the term is circumference. There's two different ways to calculate it based on what kind of measurement you're given. Either you're given the radius, in which you need to double it and then multiply it by pi, or you're given the diameter, which is, you know, double the radius. That's the relationship between r and d in this case. R being the radius, d being the diameter. Now, the radius, by definition, and this is something that I'm assuming a lot of people already have, you know, working knowledge of, the radius is the distance from the center of the circle, straight line distance, to the outer edge. The diameter is the distance from one side of the circle to the other, encompassing the center, and it's a straight line distance there as well, okay? And the relationship between a radius and a diameter is that the radius is half of the measure of the diameter, or said another way, the diameter of a circle is double the measure of its radius, okay? For every circle, forever and ever and ever, okay? Cool. So that's the circumference. That's the distance around as indicated by this red trajectory here. Whereas the area is going to be the space inside of the circle. And the way that you calculate that is that you take the radius, so again, the distance from the center of the circle to the outer edge, straight line distance, you square it and multiply it by pi. Pi, right? So hopefully we all have some kind of like introduction to this Greek letter pi. It is mathematical shorthand for an irrational number, which is for every circle ever, the ratio of the circumference to its diameter. So take this c equals pi d formula right here. If you were to divide both sides by d, you would get pi equals c over d, right? So is that true for every single circle ever and ever, no matter what the distance of circumference and diameter are for whatever circle you're talking about? Is the ratio of circumference to diameter always 3.1415926 blah 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 blah? That's the extent of my memorization of pi. Yeah, doesn't that blow your mind a little bit? For every single circle, as long as the figure is a perfect circle, the ratio of its circumference, so its distance around, the ratio of that distance to the distance through it, encompassing the center, is always 3.1415926 blah 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 forever, and it continues forever and ever and ever with no pattern whatsoever. And by that it is defined as, you know, one of the more famous quintessential irrational numbers. Crazy, right? So anyway, we usually use some kind of truncation of this in order to perform some calculations, like 3.14. Some textbooks or exercises will have you use a ratio of 22/7, which is really close, but not. pi. It's not the same. Because pi being an irrational number, it by definition cannot be represented by a ratio, and a ratio of 27 over 4 or 22 over 7 is, yeah, not going to cut it. It's pretty close though. Some people use it as an approximation. And then otherwise, if you want an exact answer that contains a factor of pi, often you are just asked to leave your answer in terms of pi, which is just having that symbol come along for the ride. So that's what's going to be asked of you pretty much all the time as far as like the exercises that I care about, and definitely on the exam 5 for sure. Okay, now we have those in play. Are there more formulas? Sure. Let's say that you wanted to just take a piece of that circumference. That would be arc length, in which case you'll take 2 pi r, one of these circumference options for that formula, and then take a ratio of it according to the degree measurement of what we call the central angle, okay? So that Q is going to be the central angle measurement. You'll divide it by 360. That'll give you the proportion of the entire circumference that you're going to need. So that's where this ratio comes from here. Okay, now what happens if you just want a piece of that area of the circle, not the whole thing? Then you'd be finding the area of the sector, and this would be like the area of this like pizza slice here, so to speak. Again, you need that central angle measurement Q, and then otherwise you just need R, right? You'll square R, multiplying it by pi. That'll give you the area of the entire circle, but then the Q over 360, that gives you the proportion of the circle that's represented by this sector. Okay, cool. I believe those are all the formulas that we need, so let's go ahead and punch out some examples. And I want you to note that some of these examples are going to reference some elements of the previous section, so definitely keep those formulas handy. We're going to find the circumference of the circle shown and give an exact answer. Whenever you see phrasing like give an exact answer or leave your answer in terms of pi, that means you're not going to bother with any kind of 3.14 anything. That pi symbol is just, like I said before, going to come along for the ride. It's just going to be a factor that gets strung along as far as the simplification goes for any of your exercises here. So here we go. First thing we want to do is reference the appropriate formula. Notice that I opted for the circumference formula of 2 times pi times r instead of pi times d. Why is that? Because the measurement that I was given was the radius. You guys see that? The distance from the center of the circle to the outer edge, that's the radius. So I want to use the 2 pi r version of the circumference formula. So I'll just plug in an 8 for my r. I'll multiply the 2 and the 8 together, and pi is just going to come along for the ride in the back end. Okay, so that's how I'll get my final answer of 16 pi inches. Now remember, circumference is like perimeter. It's a one-dimensional construct, so the units should be one-dimensional. Okay, only when we talk about area of a circle or area of a sector or composite figures that contain circle elements are we going to talk about two-dimensional units. Okay, moving on. Now, in this example, we're tasked with finding the radius of a circle given the circumference of 34 yards. Give an exact answer. So we're going to go backwards with it. We're given a circumference, and we're going to use that in order to calculate the radius. It's like the backwards version, so to speak, as far as the process is concerned, compared to the first example. Let's, of course, reference the appropriate formula. Again, I'm going to choose c equals 2 pi r because radius is the thing we're trying to solve for. So I definitely want radius to be part of that formula that I choose to use. If I chose c equals pi d, then I would have to take an extra step at the end after solving for d to cut it in half. So I'm just kind of saving myself that extra step by using the appropriate version of this formula. All right, what do we know? The circumference is 34, so go ahead and replace that with your c value and solve for r. Okay, here we go. I'm going to divide both sides by 2 pi. Yep, pi is there. Don't 3.14 it. Don't do it. Just let it stay there. And affix the appropriate units. Oh, but we can simplify the rational units. The 34 and the 2, they have a common factor of 2, so slash them away. And that'll leave just the factor of pi down below and a 17 in the numerator. Definitely you'll want to simplify anything that you can, but don't do anything with that pi. Don't call it 3.14 and reach for your calculator or anything silly like that. You're not being asked to do that. We want an exact answer, and that means leave the pi factor alone. Leave your answer in terms of pi. That's what we want. Okay? So yeah, yards is the appropriate unit, so that's why there's a YD period there. Cool. All right, moving on. Ooh. Let's find the perimeter of the figure here. Assuming the arcs are semicircles, which I want to make sure is defined here uniquely. A semicircle is exactly half of a circle, okay? So that's what these little figures right here are meant to represent. These are semicircles. So those two semicircles, if you were to match them together, watch this. It makes an entire circle. So finding the perimeter is going to be as easy as this. Find the circumference of one entire circle whose diameter is 10 centimeters, and then also add together these two 18 centimeter lengths, which I'm assuming this is also 18 centimeters. We can assume that here from the figure. And then that's the circumference. So here is my custom perimeter formula, in which I take the circumference of an entire circle of 10 centimeter diameter. So I'm going ahead and calling it a 5 centimeter radius, and I'm going 2 pi radius as my version of the circumference formula that I'm using, plus those two 18 centimeter lengths as well. Okay, and that's how I'm going to get my full perimeter. And then, yeah, I know this might feel a little bit weird, but stick with me on this, folks. Here's my perimeter, and it has two separate terms to it, and that's the final answer. Notice that the centimeters are in play. That's because I have my final answer here. If I'm going to give an exact answer, I need to keep these two terms separate because they're not like terms. One of them, the 36 centimeters, is an integer value, 36. A rational number value. Whereas this 10 pi's, that's not a rational number. 10 times pi is going to be approximately, 31.415926 forever and ever and ever, going off in some patternless additional numbers, that is. But it's not something that you can, if you're giving an exact answer, combine with this other term. So I have a rational term here and an irrational term. They need to stay separate, and then you affix the appropriate units. I know that might feel a little bit weird, but that's the way I want you to present it, okay? Cool. So in class, let me know if you have any more questions about that, because the idea of that can be a little tricky. Okay, but that one's done. Let's go ahead and move on to the next example. Let's say we were asked to find the area of the circle given. We want to give an exact answer. Notice that the diameter value is given to you, so it's your job in referencing the area formula that you need the radius. Well, if the diameter is 14 feet, how long is that radius? 7 feet, right? Just cut it in half. Cut that diameter value in half, and you have the radius. So I'm going to plug in a 7 for r, not 14, because that's the diameter. And I'll square it, and I'll get 49. The pi just follows along, okay? And becomes part of the final answer value of 49 pi feet squared, because we want to give an exact answer. We want that answer to still be in terms of pi, okay? Moving on. Let's find the diameter of a circle with an area of 500 meters squared. Give an exact answer. Here we go. Reference the appropriate formula. Plug in what you know. The area is 500 meters squared. We are set to find the diameter. Careful, diameter, not radius. Even though the formula is in terms of radius, what we're going to need to do once we calculate the value of r is we're going to have to double it to get the diameter. So keep that in mind, okay? But let's go ahead and solve for r for the moment. Let's divide both sides by pi. Let's take the square root of both sides. Woo! Right? That's nuts. And remember, we're just taking the principal square root because we're trying to find a distance here. The diameter is a distance. We're almost able to present the radius value here, but we need to simplify the radical 500 and also rationalize the denominator. So there's several algebraic steps that are going to take me from here to there. We could talk about it more in class if you want to, but basically that's the radius as an exact answer. But I'm asking for diameter, so we got to double this. What do you double? Actually, it's only the 10 factor outside of the radical that you double. Okay, so turn that 10 into a 20, double that, and that gives you the diameter, and it's in meters, so don't forget to affix the appropriate units there of meters, the little m there. Okay, cool. So there are some algebraic nuances associated with this example that I am leaving out, but we can talk about them more in class per your request. Okay, all right, moving on. Let's find the total area of the figure here. Assume each arc is a semicircle. Give an exact answer. So we want the area, the space inside. Okay, and let's recognize that these two semicircles, if I fit them together, they make an entire circle with a diameter of 6 inches. So that's the trick here, folks. If you can see that with the figure that looks like this, then you know what to do next. You're going to make your own custom area formula, which is going to be the area of the rectangle, that's this first term, and then the area of the single circle with radius 3 inches because the diameter was 6 inches. You guys see that? See how the r value that's being squared is a 3 and not a 6? So you want to be careful with that. You want to simplify, and then affix the appropriate units, recognizing that in the first level of simplification here, you can't combine the 120 and the 9 pi. The 120 is a rational term. The 9 pi is an irrational term. Don't add them together. Don't call it 129 pi. That's not correct. You don't have 120 pi's. You just have 120. And then 9 pi's over here. Don't combine them. Keep them separate. Affix the appropriate units, which will be inches squared in this case. Okay, because we're talking about area, so we know it's squared. And the distance measurement in play was inches. Okay, cool. Next one. We are going to find the length of minor arc AB. Now, minor arcs, major arcs, let's go ahead and make sure we know that what that is. So the minor arc is going to be the less than a semicircle, so less than halfway across the circle distance as far as the arc length is concerned. The major arc would be the long way around. A distance that is longer than a semicircle is the definition of a major arc. That would be the antithesis of this minor arc that's being mentioned here. So we want to find the length of the distance from A to B in this direction, encompassing this central angle of 80 degrees, and we have a radius of 16 centimeters given to us. That's all the information that we need. We need the central angle and we need the radius, and we're going to put it into this formula right here. This is the arc length formula where Q is 80 degrees and R is 16. So go ahead and plug those in and then simplify. Right? Those degree units cancel out along with a factor of 10 and at least a factor of 4, I think. So, and then also there's another factor of 2 here, several more. Yeah, so if you simplify all the way down, leaving, of course, the pi in place, you will get 64 pi over 9 centimeters. You could also have, if you wanted to, the fraction of 64 over 9 separate, pi as a standalone factor next to it. Like the pi does not need to be absorbed into the numerator necessarily. That was a stylistic choice that I made here as far as presenting my final answer. It's perfectly fine to call it 64/9 pi centimeters. That would be an alternative, totally correct way of presenting the final answer here, but just make sure that anything in regard to the fraction numerical components has to be simplified all the way down. Moving on. Area of a sector, the shaded region, shaded sector here, okay? Notice again that we have the central angle of 144 degrees. We have the radius. That's all you need. Reference the formula. There it is. Put in 144 for Q, 30 for R. Simplify, simplify, simplify. Affix the appropriate units. And remember, giving an exact answer means that your pi comes along for the ride. The area being the categorization of your units here means that you square the centimeters. Cool. Okay. Moving on, I think we're just about done. Okay, we're getting close to the end here. Let's find the area of the shaded region. So we have a composite figure here. It looks like it's a parallelogram with a big hole punched out of it, right? A hole that happens to be exactly as the height of the parallelogram itself. The height of the parallelogram, the 12 feet, happens to also be the diameter of the circle. That, I think, is probably the bit of the trick you need to be able to see in order to get through this, because you have to come up with your own custom area formula. So here's the custom area formula with the values already plugged in. So the first term is the base times height. That's the parallelogram itself. And then I'm subtracting off the area of the circle. So careful, pi r squared is the area formula for a circle, and notice that it's a 6 in for r, and that's because the diameter is what's given to you at 12 feet. The diameter is 12 feet, that means the radius is 6 feet, half of that. So that's why I have a 6 in here for the r position of my custom formula, okay? So then you simplify, oops, go back, sorry. You simplify, sorry, it was just one step of simplification, and there's nothing further that you can do. You can't actually perform the subtraction, because remember, this first term is a rational number, and this 36 pi that you're subtracting off is irrational. So you can't actually perform that subtraction if you're trying to give an exact answer. Keep that separate pi term in play. Keep it there, keep it separate, but do affix the appropriate units. It'll be feet squared for this one. And with that, we're done. These are the homework problems that I suggest that you try out, and if you have any questions on these, certainly we can go over those in class and anything that was presented in this lecture video. Cool. I look forward to seeing you soon.